There is a rock the size of the Empire State Building falling toward Earth right now, and in April 2029, you will be able to see it with your naked eyes as it slices through our satellite belt. While the world obsesses over interstellar comets wandering harmlessly near Jupiter, this thing named after the Egyptian god of chaos is closing in, kilometer by kilometer, day by day. NASA says we are safe, that the math has been checked and rechecked, but new thermal forces are pushing it off course, tiny nudges that compound over time, and the scientists who track these things are watching very, very carefully. Stay with me until the end, and I will show you why Apophis is not just another space rock, but a countdown we cannot ignore. If these questions about Apophis and our cosmic neighborhood have pulled you in the way they have pulled me in, make sure to like this video and subscribe for updates as we move closer to the most significant asteroid flyby in recorded history. Leave a comment with where you're watching from, what hour it is there right now, and your take on whether the official narrative about planetary defense is as solid as they claim it is. Picture this. Somewhere beyond Mars, a mountain of rock and metal the size of the Empire State Building is falling toward Earth at speeds that would obliterate every speed record ever set by human hands. You cannot see it yet. Most people do not even know its name. But on April 13th, 2029, this thing will arrive. It will not merely pass by our planet. It will slice through the orbital ring where our satellites live, coming so close that people in parts of Europe, Africa and Asia will be able to see it with their naked eyes as it carts across the night sky like a celestial blade. NASA has named it Apophis, after the ancient Egyptian god of chaos and destruction, and while scientists assure us that we are safe, that the calculations have been run and rerun, that the margins are known and the threat is contained, there is something they are not saying quite as loudly. The rock is drifting. New forces barely understood until recently are pushing Apophis off its predicted course. The error bars are shrinking, yes, but they have not disappeared. And in the silent mathematics of orbital mechanics, even the smallest deviation can mean the difference between a cosmic spectacle and an extinction-level catastrophe. Meanwhile, out near Jupiter, another visitor has captured the public imagination, Comet 3I Atlas, an interstellar wanderer that originated somewhere beyond our solar system, has been making headlines as it traces a path through the outer reaches of our neighborhood. It is scientifically fascinating, absolutely. Researchers are studying its composition, trying to understand what materials exist in other star systems, what the building blocks of distant worlds might look like. But here is what matters for our immediate survival. 3I Atlas poses zero threat to Earth. Its orbit keeps it millions upon millions of kilometers away from our blue marble. It is a cosmic curiosity, a visitor from the interstellar void that will pass through and leave without incident. We love to romanticize comets. They have tails that glow. They move with ethereal grace. They feel like messengers from the universe. Asteroids, by contrast, are rocks, boring, brutish chunks of debris left over from the solar system's formation. But this bias, this preference for the pretty over the practical, blinds us to which objects actually matter. Apophis matters. It has been on our radar since 2004 when astronomers first calculated its orbit and realized with growing alarm that this thing was going to come uncomfortably close to Earth. Initial estimates gave it a 2.7% chance of impact in 2029. That might not sound like much, but in the world of planetary defense, it was enough to elevate Apophis to a level 4 on the Tuino Scala, classification reserved for objects that warrant serious attention from astronomers worldwide. For a brief, terrifying moment, humanity had to confront the possibility that a chunk of space rock 340 meters across might actually hit us. Subsequent observations thankfully eliminated the 2029 impact scenario. Then they eliminated 2036. Then they eliminated every other close approach for at least a century. NASA's official position is unambiguous. Apophis will not hit Earth. The risk has been calculated, recalculated, and effectively removed from the danger list. But here is where the story gets complicated. Because while the immediate threat has been ruled out, the long-term picture is messier than the press releases suggest. Scientists have recently incorporated something called the Yarkovsky Effect into their models. This is a subtle force, almost ridiculously small on the scale of celestial mechanics, but it is real and it is measurable. When sunlight hits an asteroid, it heats one side. As that side rotates into shadow and cools down, it releases infrared radiation back into space. That radiation, faint as it is, produces a tiny push. Over decades and centuries, these tiny pushes add up. They can shift an asteroid's orbit by kilometers, sometimes more. For Apophis, scientists have now measured this effect and incorporated it into their predictions. The good news is that the uncertainty for the 2029 flyby is now razor thin, just a few kilometers. The unsettling news is that this tiny thermal force opens up questions about what else we might be missing. If sunlight itself can nudge a rock off course, what about micrometeoroids? What about gravitational interactions with other asteroids? What about forces we have not even identified yet? The media tends to present science in binary terms. Either we are safe or we are doomed. Either the threat is real or it is fake news. But the universe does not operate in binaries. It operates in probabilities, in margins of error, in unknowns that shrink only as our observations improve. Right now, the official story is that Apophis poses no danger for at least 100 years, and that is probably true. But probability is not certainty. Models are only as good as the data they are built on, and the data we have on Apophis, while extensive, is still incomplete. We do not know its internal structure. We do not know if it is a solid chunk of rock or a loosely bound pile of rubble, held together by its own weak gravity. We do not know exactly how its surface reflects and absorbs heat, which directly affects the strength of the Yarkovsky push. These are not trivial details. They are the variables that determine whether our predictions hold or crumble. So while the world watches 3I Atlas glide harmlessly through the outer solar system, a far more immediate concern is ticking down like a cosmic countdown. April 13th, 2029. Mark it on your calendar. Because on that day, whether we are ready or not, whether our models are perfect or flawed, Apophis will arrive and the whole world will be watching. This is not a distant abstraction. It is a date etched into the trajectory of a mountain sailing through the void. A date that will test our technology, our science, and our collective nerve. And it all starts with a discovery made on a summer night in 2004, when astronomers spotted a faint moving dot against the backdrop of stars and realized, with dawning unease, that it was coming our way. The story of Apophis is the story of modern planetary defense in microcosm. It is a tale of uncertainty refined into precision, of panic subdued by data, and of a lingering unease that whispers, what if we're missing something? To understand why this asteroid matters, you have to understand how we track these things in the first place. It is a process equal parts brilliant and terrifying, a high-stakes chess game played across millions of miles with rules written in calculus and gravity. When astronomers discover a new asteroid, they start with a handful of data points positions in the sky observed over several nights. From those positions, they calculate an orbit. But early orbits are rough sketches, not finished portraits. The uncertainty is enormous. The asteroid could be on a path that brings it dangerously close to Earth, or it could be on a path that keeps it safely distant. You simply cannot tell from a few nights of observation. So astronomers keep watching. Night after night, month after month, sometimes year after year, they collect more data. Each new observation narrows the uncertainty. The orbit becomes clearer. The predictions become sharper. For most asteroids, this process is straightforward. You watch, you calculate, you confirm that the object poses no threat, and you move on to the next one. But Apophis was different from the start. When it was first discovered in June of 2004, astronomers immediately recognized it as something worth monitoring closely. Its orbit brought it near Earth, and the initial calculations suggested that a future close approach was not just possible, but likely. Then on December 27th of that same year, updated observations refined the orbit, and suddenly the picture got much worse. The new calculations indicated that Apophis might actually hit Earth during its close approach on April 13th, 2029. The probability was small but non-negligible, around 2.7%. That was enough to push Apophis to that level 4 on the Torino scale. It was the first time any asteroid had reached level 4 since the scale was created. The astronomical community went into high alert. Over the following months, more observations poured in. Astronomers around the world turned their telescopes toward Apophis, gathering as much data as they could, and slowly the uncertainty shrank. By August 2005, new radar observations from the Arecibo and Goldstone facilities provided incredibly precise measurements of Apophis's position and velocity. These observations effectively ruled out the 2029 impact scenario. The asteroid would pass close, yes, but it would not hit us. The Torino scale rating dropped to 0. The immediate panic subsided. But the story was far from over, because now scientists had to consider a new wrinkle: gravitational keyholes. These are tiny regions of space, sometimes just a few hundred meters wide, through which an asteroid can pass and have its orbit altered by Earth's gravity in such a way that it returns on a collision course during a future approach. For Apophis, the concern was the 2036 encounter. If Apophis passed through a specific keyhole during the 2029 flyby, it could be nudged onto a path that brought it back for a direct hit 7 years later. This is where things get conceptually wild. Imagine playing cosmic billiards where the pockets are invisible, scattered across space, and hitting one pocket sets up a shot that might not land for decades. Gravitational keyholes are real. They have been mathematically proven, and for a brief period, Apophis seemed like it might thread one of these needles. Fortunately, additional observations ruled out that scenario as well. The 2036 impact was eliminated, then the 2068 impact. One by one, the threatening scenarios fell away as the data improved. By 2021, NASA officially removed Apophis from its risk list for at least 100 years. The message was clear: we are safe. Apophis is not going to hit us. Except that is when the Yarkovsky Effect entered the conversation. Scientists had suspected for years that thermal forces could influence asteroid orbits, but measuring the effect on a specific object required incredibly precise data. In 2021, astronomers used radar observations to detect the Yarkovsky acceleration on Apophis for the first time. They measured how much the asteroid was drifting from its predicted path due to the uneven heating and cooling of its surface. The drift was tiny, less than 200 meters per year, but it was measurable and it was real. This discovery fundamentally changed how scientists model Apophis's long-term orbit. Before, they could assume the orbit was determined purely by gravitational forces, the Sun, the planets, and other massive bodies. Now they had to account for a non-gravitational force that depends on the asteroid's size, shape, rotation rate, and surface properties, all of which are still not perfectly known. The Yarkovsky effect is not going to make Apophis hit us in 2029. The calculations are solid on that point. The uncertainty in the flyby distance is now around plus or minus 3 kilometers, which sounds like a lot until you remember that Earth itself is over 12,000 kilometers in diameter. We are not talking about a near miss. We are talking about a close pass with a known and manageable margin of error. But here is the thing that keeps planetary defense scientists up at night. The Yarkovsky effect accumulates. It is a small push, yes, but it is a constant push. Over decades and centuries, those small pushes can move an asteroid by thousands of kilometers. And if our models of the effect are even slightly wrong, if we have misjudged the asteroid's thermal properties or rotation rate by just a bit, then our predictions for encounters in 2050, 2080, or 2110 could be way off. This is not science fiction. This is the cutting edge of orbital mechanics. And it is why, even though NASA says we are safe, the scientists are still watching, still measuring, still refining. Because in space, the difference between safe and catastrophic can be measured in meters, and we are still learning how to measure. So as we stand here today with the calendar pages turning toward 2029, we are caught between two truths. One is the reassuring certainty of mathematics, which tells us Apophis will pass by without harm. The other is the humbling uncertainty of nature, which reminds us that our knowledge is always provisional, always subject to revision. The flyby in 2029 will be the ultimate test of which truth holds more weight. It will be a spectacle of science, a moment of global awe, and a silent audit of our planetary defense capabilities. And it all begins with a rock in the dark, tumbling silently toward us, carrying with it a lesson about our place in a universe that is both predictable and profoundly unpredictable. Let us talk about how we actually track these things, because the process is equal parts brilliant and terrifying. When astronomers discover a new asteroid, they start with a handful of data points, positions in the sky observed over several nights. From those positions, they calculate an orbit, but early orbits are rough sketches, not finished portraits. The uncertainty is enormous. The asteroid could be on a path that brings it dangerously close to Earth, or it could be on a path that keeps it safely distant. You simply cannot tell from a few nights of observation. So astronomers keep watching. Night after night, month after month. Sometimes year after year, they collect more data. Each new observation narrows the uncertainty. The orbit becomes clearer. The predictions become sharper. For most asteroids, this process is straightforward. You watch, you calculate, you confirm that the object poses no threat, and you move on to the next one. But Apophis was different from the start. When it was first discovered in June of 2004, astronomers immediately recognized it as something worth monitoring closely. Its orbit brought it near Earth, and the initial calculations suggested that a future close approach was not just possible, but likely. Then, on December 27th of that same year, updated observations refined the orbit, and suddenly the picture got much worse. The new calculations indicated that Apophis might actually hit Earth during its close approach on April 13th, 2029. The probability was small but non-negligible, around 2.7%. That was enough to push Apophis to a level 4 on the Torino scale, a rating system designed to communicate impact hazards to the public. Level 4 means an object that merits attention by astronomers, an event that is uncommon but not unprecedented. It was the first time any asteroid had reached level 4 since the scale was created. The astronomical community went into high alert. Over the following months, more observations poured in. Astronomers around the world turned their telescopes toward Apophis, gathering as much data as they could, and slowly the uncertainty shrank. By August 2005, new radar observations from the Arecibo and Goldstone facilities provided incredibly precise measurements of Apophis's position and velocity. These observations effectively ruled out the 2029 impact scenario. The asteroid would pass close, yes, but it would not hit us. The Torino scale rating dropped to 0. The immediate panic subsided, but the story was far from over, because now scientists had to consider a new wrinkle. Gravitational keyholes. These are tiny regions of space, sometimes just a few hundred meters wide, through which an asteroid can pass and have its orbit altered by Earth's gravity in such a way that it returns on a pulse collision course during a future approach. For Apophis, the concern was the 2036 encounter. If Apophis passed through a specific keyhole during the 2029 flyby, it could be nudged onto a path that brought it back for a direct hit 7 years later. This is where things get conceptually wild. Imagine playing cosmic billiards where the pockets are invisible, scattered across space, and hitting one pocket sets up a shot that might not land for decades. Gravitational keyholes are real. They have been mathematically proven, and for a brief period Apophis seemed like it might thread one of these needles. Fortunately, additional observations ruled out that scenario as well. The 2036 impact was eliminated. Then the 2068 impact. One by one, the threatening scenarios fell away as the data improved. By 2021, NASA officially removed Apophis from its risk list for at least 100 years. The message was clear. We are safe. Apophis is not going to hit us, except that is when the Yarkovsky Effect entered the conversation. Scientists had suspected for years that thermal forces could influence asteroid orbits, but measuring the effect on a specific object required incredibly precise data. In 2021, astronomers used radar observations to detect the Yarkovsky acceleration on Apophis for the first time. They measured how much the asteroid was drifting from its predicted path due to the uneven heating and cooling of its surface. The drift was tiny, less than 200 meters per year, but it was measurable and it was real. This discovery fundamentally changed how scientists model Apophis's long-term orbit. Before, they could assume the orbit was determined purely by gravitational forces, the Sun, the planets, and other massive bodies. Now, they had to account for a non-gravitational force that depends on the asteroid's size, shape, rotation rate, and surface properties, all of which is still not perfectly known. The Yarkovsky effect is not going to make Apophis hit us in 2029. The calculations are solid on that point. The uncertainty in the flyby distance is now around plus or minus 3 kilometers, which sounds like a lot until you remember that Earth itself is over 12,000 kilometers in diameter. We're not talking about a near miss. We are talking about a close pass with a known and manageable margin of error. But here is the thing that keeps planetary defense scientists up at night. The Yarkovsky effect accumulates. It is a small push, yes, but it is a constant push. Over decades and centuries, those small pushes can move an asteroid by thousands of kilometers. And if our models of the effect are even slightly wrong, if we have misjudged the asteroid's thermal properties or rotation rate by just a bit, then our predictions for encounters in 2050, 2080, or 2112 could be way off. This is not science fiction. This is the cutting edge of orbital mechanics, and it is why, even though NASA says we are safe, the scientists are still watching, still measuring, still refining, because in space the difference between safe and catastrophic can be measured in meters, and we are still learning how to measure. To truly appreciate the precision required, consider the concept of the impact corridor. When an asteroid is on a potential collision course, its uncertain trajectory is not a single line but a statistical cloud of possibilities, a line of variation that stretches across space. Early in the observation process, this cloud can be enormous, sometimes wide enough to envelop the entire Earth. A hit is not a certain bullseye, but the Earth being somewhere inside that cloud of probability. As data improves, that cloud shrinks. For Apophis in 2004, that cloud initially intersected Earth. That's what the 2.7% probability represented, the portion of the possible trajectories within that cloud that would result in an impact. More observations sliced away at that cloud, carving it down until the Earth was completely outside of it. The keyhole problem emerged from this same principle but on a finer scale. Even after the 2029 impact cloud was eliminated, there remained incredibly thin, filament-like paths within that cloud, the keyholes, that, if traversed, would not cause impact in 2029, but would funnel the asteroid onto a new trajectory that would intersect Earth on a later date. Eliminating the keyhole threat required shrinking the uncertainty cloud to a width smaller than the keyhole itself. Radar observations from Arecibo did exactly that, proving Apophis would miss not just Earth, but the lethal keyholes scattered around it. This is orbital surgery at a distance of millions of miles. It is humanity using the echo of a radar pulse to map a mountain in the void and prove it will pass through a gap tens of thousands of kilometers wide, while avoiding specific pinholes only hundreds of meters across within that gap. The achievement is staggering. Yet the Yarkovsky effect introduces a slow, persistent pressure that warps this cloud of possibilities over long time scales. It doesn't just move the predicted centerline of the trajectory, it can also subtly change its shape and orientation. This is why long-term prediction is so fraught. We're not just calculating where the asteroid is now and projecting it forward with gravity. We are trying to account for a gentle, continuous thrust whose exact magnitude and direction we must infer from limited data. It is like predicting the path of a sailboat across an ocean decades into the future, where we know the currents and tides, gravity, with great accuracy, but can only estimate the wind, Yarkovsky, by observing the boat's drift over a few days. A small error in our estimate of that wind can steer the predicted course miles away from the actual destination. For Apophis, the destination in question is not a 2029 impact, but its trajectory after 2029. The close encounter with Earth will dramatically alter its orbit, a gravitational slingshot that will send it onto a new path around the Sun. The Yarkovsky effect, acting before, during, and after that encounter, influences precisely where that new path will point. Get the Yarkovsky parameters wrong, and our map of its future and its potential to re-enter a keyhole in a future century becomes unreliable. This is the silent mathematical drama unfolding in observatories and supercomputing centers right now. It is a drama without villains or heroes, only data and error bars. Each new observation of Apophis, whether from an optical telescope measuring its reflected sunlight or a radar dish pinging it with microwaves, is fed into these ever-evolving models. The goal is not just to reassure the public for the next flyby, but to build a predictive framework so robust that we can see threats coming centuries in advance. Apophis is our training ground, our laboratory, and our wake-up call. It taught us that initial scare, the process of refining a threat, the discovery of keyholes, and now the intricate dance of non-gravitational forces. Every lesson learned from tracking this one rock makes us more capable of protecting ourselves from the next one. Because the mathematics of near misses is not just about Apophis, it is the foundational language of our survival as a species in an active solar system. It translates the silent motion of rocks in the dark into probabilities, timelines, and, ultimately, actionable knowledge. The numbers tell a story. For 2029, the story is one of a spectacular near miss. But the same numbers, stretched across a longer narrative, whisper a cautionary tale about the limits of our foresight and the persistent, subtle forces that write the future in ways we are only beginning to read. April 13th, 2029. Let that date sink in for a moment. It is not some distant future abstraction. It is less than 5 years away. People who are in high school right now will be starting careers. Children who are just learning to read will be teenagers. And on that day, something will happen that no human civilization has ever witnessed with modern technology. A mountain-sized asteroid will pass so close to Earth that it will fly underneath our geostationary satellites. We're not talking about a distant speck visible only through telescopes. We're talking about an object that will be bright enough to see with the naked eye, cruising across the sky like a slow-moving star, visible from Europe, Africa, and Western Asia. People will be able to walk outside, look up, and watch as 340 meters of primordial rock slides past our planet at a distance of roughly 31,000 kilometers. That is closer than the orbit of most communication satellites. It is closer than the GPS network. It is so close that Earth's gravity will physically affect the asteroid, potentially changing its rotation rate and reshaping its surface. To put this in perspective, consider what 31,000 kilometers actually means. The International Space Station orbits at about 400 kilometers up. The geostationary satellite belt, where most of our communication and weather satellites live, sits at roughly 35,786 kilometers. Apophis will pass between Earth and that satellite belt. It will thread the gap. Now, before you panic, scientists have calculated the trajectories and confirmed that Apophis will not hit any satellites. Space is big, even in the crowded regions near Earth, and the chances of a direct collision are vanishingly small. But the symbolic and practical implications are staggering. We have built a technological infrastructure in orbit that our modern civilization depends on. Television, internet, GPS, weather forecasting, military communications, all of it relies on satellites that orbit in that ring. And for the first time in history, a natural object large enough to cause regional devastation if it hit Earth will pass through that zone. It will be a visceral demonstration of how thin the membrane is between our terrestrial world and the raw cosmos. Our satellites, the pinnacle of our engineering, will be looking up at a passing mountain that predates our planet. Astronomers predict that Apophis will reach a peak brightness of around magnitude 3.1 during the closest approach. For those unfamiliar with astronomical magnitude scales, that is roughly as bright as the stars in the Big Dipper, not blindingly brilliant, but easily visible to anyone with clear skies and a decent view of the horizon. The asteroid will move relatively slowly across the sky, not streaking like a meteor, but crawling like a satellite. It will be surreal. Imagine standing outside on a spring evening, looking up and seeing a moving point of light that you know is a rock the size of a skyscraper, passing close enough that if Earth's gravity were just a bit stronger, or if the timing were just a bit different, it could be pulled into a collision course. That is the reality of April 13th, 2029. It is not a drill. It is not a simulation. It is happening. The scientific community is treating this encounter as an unprecedented opportunity. NASA has already announced plans to send the OSIRIS-APEX spacecraft to rendezvous with Apophis shortly after the 2029 flyby. OSIRIS-APEX is the renamed OSIRIS-REx mission, which successfully collected samples from the asteroid Bennu and returned them to Earth. After completing that mission, NASA redirected the spacecraft toward Apophis. The plan is for OSIRIS-APEX to arrive at Apophis in 2029, study how the close encounter with Earth has affected the asteroid, and gather data on its composition, structure, and rotation. Meanwhile, the European Space Agency is developing its own mission called Ramses, which is designed to observe Apophis before, during, and after the flyby. These missions will give scientists an unprecedented look at how a planetary close encounter affects an asteroid in real time. It is like getting a front-row seat to a natural experiment that happens once in a millennium. They will measure the tidal forces stretching the asteroid, listen for the seismic tremors of shifting boulders on its surface, and map the changes in its spin. The data will be a goldmine for planetary science and for planetary defense. We will learn firsthand how an asteroid's physical structure responds to extreme gravitational stress, knowledge that is absolutely critical if we ever need to push one off course. But beyond the science, there is a deeper psychological impact to consider. For most of human history, the sky has been a distant, untouchable realm. The stars, the planets, the moon, were objects of wonder and mythology, things that affected us only indirectly through gravity and light. But in 2029, that separation collapses. The cosmos will reach down and touch our orbital infrastructure. An object from the primordial solar system, a relic from the age of planetary formation, will pass close enough that its trajectory will be visibly altered by our planet's gravity. Earth will pull on Apophis, and Apophis will pull on Earth. The forces are mutual, even if the effects are asymmetric. This is not a distant abstraction. This is a physical interaction between our world and the void, and it raises an uncomfortable question. If this rock can come so close without hitting us, what about the next one? What about the ones we have not found yet? What about the ones that will not give us decades of warning? Because here is the uncomfortable truth. Apophis is only as well studied as it is because we got lucky. We found it early. We had time to observe it, to refine the orbit, to rule out the impact scenarios. But there are thousands of near-Earth asteroids out there, and we have not catalogued all of them. Some are in orbits that make them difficult to detect. Some are dark, reflecting very little sunlight. Some approach from directions where our telescopes are not looking. And while the odds of any single asteroid hitting Earth in our lifetimes are low, the odds of an impact happening eventually are 100%. It is not a question of if, it is a question of when and whether we will be ready. The 2029 flyby will be a global event. It will unify humanity under a single silent point of light moving across the sky. For a few hours, billions of people will share the same view, the same thought, the same primal awareness of our place in a shooting gallery. It will be awe-inspiring and humbling. It will force a conversation that has been confined to scientific papers and defense conferences into living rooms and public squares. What are we doing to protect ourselves? How prepared are we? The spectacle of Apophis will be a powerful teacher. It will make the threat concrete in a way no statistic ever could. For scientists, the days surrounding the flyby will be a frenzy of coordinated observation. Every major telescope on Earth, and many in space, will be trained on that patch of sky. Radar installations will ping the asteroid continuously, mapping its surface topography in real time as it is distorted by tidal forces. Spectrometers will analyze the sunlight reflected from its surface, looking for changes in mineral composition as fresh material is exposed by landslides. The data torrent will be immense, and it will take years to fully analyze. But the immediate takeaway will be clear. We survived a close pass. Our models were right. But the next step in the conversation will be, will our models always be right? And what do we do when they are not? The flyby is not an end, it's a beginning. It is the starting pistol for the next phase of human history, the phase where we move from passive observers of the cosmos to active managers of our planetary environment. Apophis is the herald of that transition. It is a reminder written in rock and gravity that our childhood as a species, sheltered and unaware of the dangers beyond our atmosphere, is coming to an end. Our adulthood begins with watching the sky, understanding its dangers, and learning how to step aside. Scientists like to talk about Apophis as a learning opportunity, and they are absolutely right to frame it that way. But let us be clear about what we are actually going to learn and what remains frustratingly unknown. The 2029 encounter will provide data that we simply cannot get any other way. When Apophis passes through Earth's gravitational field, our planet will exert tidal forces on the asteroid. These are the same forces that cause ocean tides, the stretching and squeezing that occurs when a massive object like the Moon pulls on different parts of Earth with slightly different strengths. For Apophis, which is much smaller and less massive than Earth, the effect will be more pronounced. Earth's gravity could change the asteroid's rotation rate. It could cause surface materials to shift or slide. It could even trigger small landslides if the asteroid is a loosely bound rubble pile rather than a solid chunk of rock. Scientists will be watching all of this with radar and optical telescopes, measuring every wobble, every shift, every tiny change. This data will help answer fundamental questions about asteroid composition and structure. Is Apophis monolithic or fractured? Is it dense and metallic or porous and rocky? How much of its mass is locked in a solid core versus scattered in a loose shell? These are not academic curiosities. They are practical questions that directly impact planetary defense. If we ever need to deflect an asteroid, the method we choose depends entirely on what that asteroid is made of. A solid rock can be nudged with a kinetic impactor, a spacecraft that slams into the surface and transfers momentum. But a rubble pile might just absorb the impact, letting the fragments drift apart before gravity pulls them back together. Understanding asteroid structure is critical to developing effective defense strategies, and Apophis, because of its close pass, will give us that understanding in ways that distant observations never could. But here is what the flyby will not tell us: whether Apophis poses a long-term threat. The 2029 encounter is a single data point. It will refine our models, yes. It will reduce uncertainties, absolutely. But it will not eliminate the possibility of a future impact decades or centuries from now, because orbital mechanics is fundamentally a chaotic system. Small changes now can produce large effects later. This is the essence of chaos theory, the mathematical framework that describes systems where tiny differences in initial conditions lead to wildly divergent outcomes. Apophis is part of such a system. Its orbit is influenced by the Sun, by Earth, by Venus, by Jupiter, by Mars, by countless other objects in the solar system. Each influence is small, but they add up over time. And while we can model these influences with impressive accuracy, our models are not perfect. They cannot be. We do not know the exact mass of every asteroid, the exact position of every planet, the exact strength of every gravitational pull. We approximate, we estimate, we refine, but we do not know with absolute certainty. This brings us back to the concept of gravitational keyholes, which deserve a deeper examination. A keyhole is a region of space, typically just a few hundred meters across, through which an asteroid can pass during one encounter and have its orbit altered in such a way that it returns on a collision course during a future encounter. Think of it as a cosmic game of pinball where hitting a specific bumper sets up a shot toward Earth. For Apophis, scientists have calculated the locations of several keyholes associated with the 2029 flyby. If the asteroid passes through one of these keyholes, it could return on a dangerous trajectory in 2036, 2068, or some other future date. The good news is that current models show Apophis will not pass through any known keyholes. The bad news is that keyholes are defined by our understanding of orbital mechanics, and if that understanding is incomplete, then so is our map of where the keyholes are. And then there is the Yarkovsky Effect, which we keep coming back to because it refuses to behave like a simple, predictable force. The strength of the Yarkovsky push depends on factors that we cannot measure from Earth. It depends on the asteroid's thermal inertia, which is a measure of how quickly its surface heats up and cools down. It depends on the surface roughness, the color, the composition, the rotation rate. All of these variables feed into a complex equation that determines how much the asteroid drifts over time. Scientists have made their best estimates based on the data available, and those estimates are good, but they are not perfect. And over decades, small errors in the Yarkovsky calculation can compound into significant orbital uncertainties. This is why scientists are planning to observe Apophis intensively in the years leading up to 2029. The more data they collect, the better they can constrain the Yarkovsky effect. The better they constrain the Yarkovsky effect, the more accurately they can predict future encounters. It is a process of iterative refinement, and it never truly ends. But there is another factor that barely gets mentioned in the public discussions, and it is perhaps the most unsettling of all. The possibility of a collision with another object. Space is not empty. It is filled with debris from tiny dust grains to larger rocks and even other asteroids. Most of this debris is too small to track, and the odds of any single collision are incredibly low. But over the timescales, we are talking about decades and centuries. The cumulative probability becomes non-negligible. If Apophis were to be struck by even a small meteoroid at the right angle and velocity, it could change the asteroid's trajectory in ways that our models did not anticipate. This is not fear-mongering. This is acknowledged in the scientific literature. Researchers have studied the statistical likelihood of such events and concluded that while rare, they are not impossible. And in a chaotic system, the impossible merely means we have not seen it happen yet. So yes, the 2029 flyby will teach us an enormous amount about Apophis. It will refine our models, reduce our uncertainties, and give us confidence in our predictions for at least the next several decades. But it cannot eliminate all doubt because the universe is not obligated to fit neatly into our equations. And the margin between certainty and catastrophe is thinner than most people realize. This is the sobering reality of living in a dynamic solar system. We are building a wall of knowledge against a sea of uncertainty. Every observation is a brick in that wall. The Apophis flyby will add some of the strongest, most precise bricks we have ever placed, but the wall is never finished. There are always gaps, always cracks, always the potential for a wave we didn't see coming to wash over the top. The goal of planetary defense is not to achieve perfect, eternal certainty. That is impossible. The goal is to build a wall so high and so strong that the probability of a breach in our lifetime or our children's lifetimes becomes acceptably small. The flyby is a critical stress test of that wall. It will show us how well our predictions hold up under extreme conditions. It will reveal weaknesses in our understanding, and it will give us the chance to patch those weaknesses before a real crisis arrives. What we learn from Apophis will not just be about one asteroid. It will be a template for how we assess and respond to all future threats. It will validate or force us to revise the very tools we use to safeguard our world. That is the true value of the encounter. Not just the answers it provides, but the better questions it will teach us to ask. Now, let us zoom out for a moment and put this entire situation into a broader context, because while Apophis dominates the conversation about near-Earth threats, it is hardly the only object we need to worry about. In fact, it is not even the most statistically dangerous asteroid currently on our radar. There are thousands of near-Earth objects, asteroids, and comets whose orbits bring them into the vicinity of Earth's path around the Sun. NASA's Center for Near-Earth Object Studies tracks these objects, calculating their orbits, assessing their potential threat, and publishing regular updates on which ones merit close attention. At any given time, there are dozens of objects with non-zero impact probabilities in the coming decades. Most of these probabilities are vanishingly small, fractions of a percent or less, but they are not zero. And in the calculus of planetary defense, non-zero is all that matters. Take, for example, the asteroid Bennu, which was visited by NASA's OSIRIS-REx spacecraft. Bennu is slightly larger than Apophis, about 500 meters in diameter, and it has a small but measurable chance of impacting Earth in the late 2100s. The cumulative probability across all potential impact dates is roughly 1 in 2,700. That is higher than Apophis's current impact probability for any future encounter. Should we be more worried about Bennu? Statistically, yes. But Bennu's potential impacts are more than a century away, whereas Apophis will make its close pass in less than 5 years. The immediacy of Apophis captures our attention in ways that distant probabilities do not. This is a quirk of human psychology. We fear what is near more than what is likely. It is why people are more afraid of airplane crashes than car accidents, even though cars are far more dangerous. It is why Apophis gets headlines while Bennu gets scientific papers. And then there is 3I Atlas, the interstellar comet that sparked this entire conversation. Let us be absolutely clear. 3I Atlas poses no threat to Earth. Its orbit keeps it in the outer solar system, millions of kilometers from our planet. It will not come close. It will not impact. It is scientifically interesting because it originated outside our solar system, giving us a rare opportunity to study material from another star's planetary system. But in terms of danger, it is irrelevant. The reason it captures public attention is the same reason comets have always captured public attention. They are beautiful. They have tails. They move across the sky with a sense of purpose and drama. Asteroids, by contrast, are just rocks. They do not blow. They do not stream gas and dust. They are harder to see, harder to romanticize, and harder to get excited about. But from a planetary defense standpoint, asteroids are what matter. They are the objects that cross Earth's orbit. They are the objects with impact potential. They are the objects with impact potential. They are the objects we need to track. The distinction between comets and asteroids is not just aesthetic, it is also about predictability. Asteroids, generally speaking, are inert. They do not outgas. They do not change mass as they move through space. Their orbits are determined purely by gravity, which makes them relatively straightforward to model. Comets, on the other hand, are active. As they approach the Sun, they heat up and release gas and dust, creating the iconic tails that make them so visually striking. But that outgassing also produces forces that change the comet's orbit in unpredictable ways. Every time a comet passes near the Sun, it loses mass, changes shape, and potentially alters its trajectory. This makes long-term predictions much harder for planetary defense purposes. This is a problem. If we cannot predict where a comet will be decades from now, we cannot assess whether it poses a threat. Fortunately, most comets do not cross Earth's orbit. They travel in elongated paths that take them far from the inner solar system, but some do, and those are the ones we watch closely. There is another class of objects that barely gets mentioned in public discussions, but keeps scientists awake at night: the unknowns. Despite decades of surveys and observations, we have not catalogued every near-Earth object. We have found most of the large ones, the asteroids bigger than a kilometer across, but smaller objects in the 100 to 500 meter range are harder to detect. They reflect less light. They are often in orbits that make them difficult to observe. And yet, an object in that size range could still cause regional devastation if it hit Earth. Imagine a city-sized asteroid striking a populated area. The death toll would be in the millions. The economic damage would be incalculable. The psychological impact would reshape how humanity thinks about its place in the universe. And we would have no warning if the object approached from a blind spot, if it came from the direction of the Sun where telescopes cannot look, or if it simply slipped through the gaps in our survey coverages. This is not meant to inspire panic. It is meant to inspire preparation. The good news is that planetary defense is a real and growing field. Telescopes are getting better. Surveys are getting more comprehensive. Machine learning algorithms are helping astronomers sift through massive datasets to find objects that might otherwise go unnoticed. And missions like DART, NASA's Double Asteroid Redirection Test, have demonstrated that we can, in principle, change an asteroid's orbit if we need to. The bad news is that we're still playing catch-up. We are still finding new objects. We are still refining new objects. We are still refining our models. We are still learning what we do not know. And in the realm of cosmic threats, what we do not know can absolutely hurt us. So yes, Apophis is the headline. It is the object that will pass close in 2029. The object that will be visible to billions of people. The object that will force humanity to confront the reality of near-Earth threats in a visceral, undeniable way. But it is not the whole story. It is one chapter in a much larger narrative about our species learning to navigate a universe that is beautiful, fascinating, and occasionally very dangerous. Our task is to balance the awe inspired by a comet like 3I Atlas with the pragmatic vigilance required by rocks like Apophis and Bennu. We must enjoy the beauty of the cosmos while diligently building the defenses that allow us to continue enjoying it. The context of cosmic threats is a spectrum from the harmless interstellar visitor to the close approaching laboratory, to the statistically risky distant threat, to the complete unknown lurking in the dark. Our response must be equally spectrum-wide, from pure scientific curiosity to intensive study and modeling to technology development and ultimately to the construction of a robust, global detection and defense system. Apophis sits in the middle of that spectrum, a perfect catalyst for action. It is close enough to be urgent but safe enough to be studied. It is the bridge between abstract risk and concrete reality, and by understanding its place in the wider context of cosmic threats, we can begin to build a sensible, proportional, and effective strategy for preserving our future on this pale blue dot. Let us talk about the forces you cannot see, the subtle pushes and pulls that govern the motion of asteroids over timescales longer than human civilizations. When most people think about orbits, they imagine a simple system, a rock going around the sun pulled by gravity following a predictable ellipse, and for short timescales that picture is basically correct. But zoom out to decades, centuries, millennia, and the picture becomes vastly more complicated because gravity is not the only force at play. There are thermal effects, there are impacts from tiny debris, there are radiation pressures, there are electromagnetic interactions. Each one is small. Each one, taken individually, might shift an asteroid's orbit by mere meters per year. But over long enough timescales, these small forces compound into significant changes. And this is where our predictions start to wobble. The Yarkovsky Effect, which we have mentioned repeatedly, is the poster child for these subtle forces. It works like this. As an asteroid rotates, one side faces the sun and heats up. Hours later, as that side rotates into shadow, it cools down and radiates infrared energy back into space. That radiation carries momentum. And because the hot side is radiating more energy than the cool side, the net effect is a tiny thrust in one direction. For a spinning asteroid, the direction of the thrust depends on whether the asteroid is rotating in the same direction as its orbit or the opposite direction. If it is rotating prograde, the thrust pushes it outward from the sun. If it is rotating retrograde, the thrust pushes it inward. The magnitude of the thrust depends on the asteroid's size, rotation rate, surface temperature, and thermal inertia. And because we do not have perfect measurements of all these properties, we have to estimate, which means our predictions carry uncertainty. For Apophis, scientists have measured the Yarkovsky drift at roughly 170 meters per year along the asteroid's orbit. That might sound small, but over the course of a 20-year observation arc, that is a shift of several kilometers, and over a century, it is tens of kilometers. Now, tens of kilometers might still sound negligible compared to the vast distances in space, but remember, gravitational keyholes are only a few hundred meters across. If the Yarkovsky effect pushes Apophis even slightly off the predicted path, it could mean the difference between missing a keyhole entirely and threading right through it. This is why scientists are so focused on refining the Yarkovsky measurements, because in orbital mechanics precision matters and uncertainty is the enemy. But the Yarkovsky effect is just one piece of a much larger puzzle. There is also something called the YOR effect, which stands for Yarkovsky-O'Keefe-Radzievský-Petak, named after the scientists who first described it. URP is related to Yarkovsky, but operates on the asteroid's rotation rather than its orbit. When an irregularly shaped asteroid absorbs sunlight and radiates it as heat, the uneven distribution of thermal radiation can create a torque that speeds up or slows down the asteroid's spin. Over millions of years, yaw can cause an asteroid to spin faster and faster until it literally flies apart, or it can slow the spin until the asteroid becomes tidally locked with the Sun. For Apophis, yaw P is less of a concern than Yarkovsky because the timescales are longer, but it is still a factor that scientists have to account for when modeling the long-term evolution of the asteroid's orbit and rotation state. And then there are the truly chaotic elements: gravitational interactions with other asteroids, collisions with micrometeorites, and even solar wind pressure. Let us start with gravitational interactions. The asteroid belt is not a tightly packed ring of rocks. It is a sparse cloud where individual asteroids are separated by millions of kilometers, but occasionally two asteroids pass close enough to each other that their mutual gravity produces a measurable tug. For most asteroids, these interactions are negligible, but for objects in the inner solar system where encounters with planets are more frequent, the cumulative effect of many small gravitational nudges can add up over time. Apophis, because of its close approach to Earth in 2029, will experience a significant gravitational interaction with our planet. Earth's gravity will change Apophis's orbit, shifting it onto a slightly different path than it was on before the encounter. Scientists have calculated this shift and determined that it will not send Apophis on a collision course. But it is a reminder that orbits are not static, they evolve. Now let us talk about impacts. Space is not empty, it is filled with debris. Most of it is tiny, dust grains and pebbles left over from the formation of the solar system, or ejected from comets as they pass near the Sun. These particles are too small to track individually, but they are numerous enough that collisions happen all the time. When a micrometeorite strikes an asteroid, it transfers momentum. The effect is minuscule. A single grain of dust hitting a 340-meter asteroid is like a mosquito hitting a freight train, but over millions of years, countless impacts accumulate, and if one of those impacts happens to occur at just the right moment, at just the right angle, it could nudge the asteroid onto a slightly different trajectory. The odds of this happening in a way that significantly affects Apophis's orbit in the next century are low, but they are not zero. This brings us to a fundamental truth about orbital mechanics. Prediction is an exercise in managing uncertainty. We can model the major forces, we can account for the big players, the Sun, the planets, the moons. We can measure the Yarkovsky effect, calculate the gravitational perturbations, and estimate the impact of solar radiation pressure. But we cannot account for everything. There are forces we do not fully understand. There are interactions we have not measured. There are variables we have not even identified. And in a chaotic system, unaccounted variables can lead to unexpected outcomes. This does not mean our models are useless. Far from it. Our models are incredibly accurate over the timescales we care about most. But they are not infallible, and the further into the future we try to predict, the more the uncertainties grow. So when NASA says that Apophis poses no threat for at least 100 years, they are not lying. They are speaking based on the best data and models available. But embedded in that statement is an acknowledgement that the 100-year horizon is roughly the limit of our predictive confidence. Beyond that, the uncertainties become too large to make definitive claims. This is why planetary defense is an ongoing process, not a one-time calculation. We have to keep watching, keep measuring, keep refining, because the universe is not static and neither are our predictions. Every new observation of Apophis, every refined measurement of its rotation, every radar echo that maps its shape, is fed back into the models, tightening the error bars and extending the window of reliable prediction. It is a never-ending conversation between the asteroid and our instruments, a dialogue conducted across millions of miles in the language of physics. We ask a question with a radar pulse. Apophis answers with an echo. We translate that echo into a data point, and our understanding of its future shifts, ever so slightly. This is the painstaking, unglamorous work that keeps us safe. It is the recognition that in the cosmic dance, our partner is a tumbling rock subject to influences we are only beginning to catalogue. Our job is to learn the steps, anticipate the turns, and be ready to move when the music changes. Here is a question that rarely gets asked outside of specialized conferences. What happens when the number of objects we need to track exceeds the capacity of human astronomers to track them? We're already approaching that threshold. There are currently over 32,000 known near-Earth objects, and the number grows every month as surveys improve and new telescopes come online. Each of these objects has an orbit that needs to be calculated, refined, and monitored for potential threats. Each one produces a stream of observational data, positions, brightnesses, spectra, radar echoes. And each piece of data needs to be analyzed, cross-referenced, and integrated into a constantly updating model of the object's trajectory. Doing this for 32,000 objects is manageable. Barely. Doing it for 100,000 or a million is not, at least not with traditional methods. Enter artificial intelligence. Over the past decade, machine learning algorithms have revolutionized how we process large datasets in astronomy. AI can sift through thousands of telescope images in seconds, identifying objects that move against the background stars, flagging potential near-Earth asteroids, and even calculating preliminary orbits. These systems do not get tired. They do not get bored. They do not miss subtle patterns because they were distracted or overworked. They are relentless, tireless pattern recognition engines that excel at exactly the kind of repetitive, data-intensive tasks that bog down human astronomers, and they are getting better every year. Modern AI systems can now detect asteroids in telescope images with accuracy rates that rival or exceed human observers. They can predict orbital uncertainties more quickly than traditional numerical methods. They can even identify anomalies, objects whose behavior does not fit expected patterns, which might indicate something unusual is happening. But AI is not just about speed and scale, it is also about prediction. Remember, orbital mechanics is a chaotic system. Small changes in initial conditions can lead to large differences in outcomes. Traditional models handle this by running thousands or millions of simulations, tweaking the initial parameters slightly each time, and then analyzing the distribution of results to estimate probabilities. This works, but it is computationally expensive and time-consuming. Machine learning offers a different approach. Instead of simulating every possible outcome, an AI can be trained on existing orbital data to recognize patterns and relationships that humans might miss. It can learn, for example, how different combinations of orbital parameters and physical properties lead to specific long-term outcomes. And once trained, it can make predictions much faster than traditional simulations. This is not science fiction. Researchers are already using machine learning to predict asteroid trajectories, and the results are promising. But here is where things get philosophically interesting. If we start relying on AI to predict cosmic threats, are we actually understanding the physics, or are we just outsourcing the problem to a black box? This is a real concern among some scientists. Machine learning models, especially deep neural networks, are notoriously opaque. They can produce accurate predictions without providing any insight into why those predictions are correct. You feed in data, you get out a result, and the internal logic that connects the two is buried in layers of mathematical transformations that no human can fully interpret. For some applications, this opacity is acceptable. For planetary defense, it is more problematic, because if an AI predicts that an asteroid has a 10% chance of hitting Earth in 50 years, we need to understand where that prediction comes from. We need to be able to interrogate the model, test its assumptions, and verify its reasoning. Otherwise, we're making decisions about humanity's survival based on a system we do not fully understand. There is also the risk of overfitting, a common problem in machine learning where a model learns to recognize patterns in the training data that do not generalize to new situations. Imagine an AI trained on a dataset of well-observed asteroids with predictable orbits. It might learn to make accurate predictions for similar objects. But what happens when it encounters an asteroid with unusual properties? An object that behaves in ways not represented in the training data. The model might confidently produce a prediction that is completely wrong. This is not a hypothetical concern. It has happened in other domains where AI is used for prediction, and in the context of planetary defense, a wrong prediction could be catastrophic. Despite these concerns, the integration of AI into planetary defense is not just likely, it is inevitable. The volume of data we are collecting is growing too fast for traditional methods to keep up. Telescopes like the Vera C. Rubin Observatory, which is set to begin operations soon, will generate terabytes of data every night, imaging the entire visible sky every few days. Human astronomers cannot possibly analyze all of that data manually. AI will have to do the heavy lifting. The question is not whether we would use AI, but how we will use it responsibly. How do we build systems that are transparent, interpretable, and robust? How do we validate AI predictions against independent observations? How do we ensure that the algorithms we deploy are trained on diverse, representative datasets that capture the full range of possible asteroid behaviors? These are the questions that planetary defense researchers are grappling with right now. And then there is the longer-term vision, the idea of autonomous AI systems that do not just analyze data, but actively manage planetary defense. Imagine a network of telescopes, radar systems, and spacecraft controlled by an AI that continuously monitors the sky, detects new threats, calculates trajectories, and even coordinates deflection missions if necessary. Such a system could react faster than human decision-making processes, potentially identifying and neutralizing threats before they become critical. But it also raises profound ethical and practical questions. Who controls the AI? What happens if it makes a mistake? What safeguards do we put in place to prevent misuse? These are not questions we can afford to ignore because the technology to build such systems is already within reach. And as Apophis reminds us, the threats are real. We are building a new kind of sentry for our Planet One, made of silicon and code. Its vigilance will be superhuman, but its judgment must be guided by human wisdom. The future of threat detection is a partnership, not a replacement. It is about amplifying our own abilities with a tool that can see farther, process faster, and connect dots we might otherwise miss. In the silent watch against the dark, AI will be our newest, most powerful eye. Let us talk about what happens if we actually need to do something about an incoming asteroid, not Apophis, because the threat there has been ruled out for the foreseeable future. But imagine we discover a new object tomorrow, a previously unknown asteroid on a trajectory that will bring it uncomfortably close to Earth in, say, 20 years. What do we do? The answer depends on a sprawling global infrastructure of telescopes, observatories, space agencies, and international organizations that collectively make up what we call planetary defense. And while this infrastructure is impressive, it is also incomplete, underfunded, and not as coordinated as you might hope. The first line of defense is detection. We cannot protect ourselves from threats we do not know about. This is why asteroid surveys exist. Telescopes around the world scan the sky night after night, looking for objects that move against the fixed background of stars. When a new object is found, astronomers calculate its orbit and determine whether it poses any threat. Most objects do not. They're either too far away, or their orbits do not bring them close to Earth, or they are so small that even a collision would not cause significant damage. But occasionally a survey finds something worrying. An object on a trajectory that crosses Earth's orbit, an object large enough to cause regional or global devastation, an object that might, if the calculations are right, actually hit us. That is when the second line of defense kicks in: international coordination. The International Asteroid Warning Network, IAWN, is a coalition of space agencies and observatories that share data and coordinate responses to potential threats. If a dangerous asteroid is discovered, IAWN facilitates the flow of information between organizations, ensuring that everyone has access to the latest observations and calculations. There is also the Space Mission Planning Advisory Group, SMPAG, which is responsible for planning and coordinating potential deflection missions. These groups do not have the authority to launch missions on their own. They are advisory bodies, but they provide a framework for cooperation, which is critical in a situation where a single country or agency might not have the resources to respond alone. Now let us talk about deflection. If we identify an asteroid on a collision course with Earth, and we have enough warning time, we can potentially change its orbit. The most straightforward method is a kinetic impactor. You build a spacecraft, accelerate it to high speed, and crash it into the asteroid. The impact transfers momentum, giving the asteroid a tiny shove. If you do this years or decades before the predicted collision, that tiny shove can be enough to make the asteroid miss Earth entirely. NASA demonstrated this technology in 2022 with the DART mission, which successfully altered the orbit of the asteroid Dimorphos by crashing a spacecraft into it. The mission was a proof of concept, showing that kinetic impact is a viable method for asteroid deflection. But it also revealed how much we still do not know. The amount of momentum transferred depends on the asteroid's composition, structure, and how it responds to the impact. Dimorphos, as it turned out, behaved more like a rubble pile than a solid rock, which changed the efficiency of the deflection. For larger asteroids or for scenarios where we have less warning time, kinetic impactors might not be enough. In those cases, scientists have proposed other methods: gravity tractors, nuclear deflection, or even laser ablation. A gravity tractor works by parking a spacecraft near the asteroid and using the spacecraft's own gravity to slowly pull the asteroid onto a different path. This method is slow but precise, making it ideal for fine-tuning an asteroid's trajectory. Nuclear deflection, on the other hand, is the option of last resort. You detonate a nuclear device near the asteroid, not to blow it up, but to vaporize a layer of surface material. The vaporized material shoots off into space, creating a thrust that pushes the asteroid in the opposite direction. It sounds like science fiction, but the physics is sound. The problem is that nuclear deflection is risky, politically fraught, and requires technology that we have not fully developed yet. But here is the uncomfortable truth. All of these methods assume we have years or decades of warning. If we discover an asteroid only months before impact, there is very little we can do. We do not have the technology to build and launch a deflection mission on such short notice. And even if we did, the asteroid would be moving too fast and too close to deflect effectively. In that scenario, our only option is evacuation and damage mitigation. We move people out of the impact zone. We stockpile resources. We prepare for the aftermath. It is not a solution. It is a band-aid. And it underscores why detection is so critical. The earlier we find a threatening asteroid, the more options we have. There are also gaps in our detection capabilities that rarely get discussed publicly. Most asteroid surveys focus on the night sky, which means they cannot see objects that approach from the direction of the sun. This is not a minor oversight, it is a significant blind spot. An asteroid coming from the sunward direction would be invisible to ground-based telescopes until it was very close, potentially too close to deflect. This is exactly what happened with the Chelyabinsk meteor in 2013, a 20-meter object that exploded over Russia without warning because it approached from the direction of the sun. The explosion released energy equivalent to about 500 kilotons of TNT, injured over 1,000 people, and caused widespread property damage. And we never saw it coming. Chelyabinsk was small, too small to cause global devastation, but it was a wake-up call. It demonstrated that our detection network has holes, and those holes could be exploited by larger, more dangerous objects. The solution, according to many planetary defense advocates, is to put telescopes in space. A space-based infrared telescope, positioned at a point between Earth and the Sun, could detect asteroids approaching from the sunward direction, closing the gap in our detection coverage. NASA has proposed such a mission called NEO-Surveyor, which is designed to find and track near-Earth objects using infrared sensors. The mission is still in development with a tentative launch date in the late 2020s. If it succeeds, it will significantly improve our ability to detect threats. But until it launches, the blind spot remains, and so does the risk. Our planetary defense infrastructure is a shield still under construction. We have laid the foundation with detection surveys and international groups. We have tested one tool in our workshop with DART, but the shield is full of gaps, and we have not yet forged all the tools we might need. The clock is ticking, not just for Apophis, but for the thousands of unknown rocks whose paths we have not yet charted. Building a complete defense is a race against time and probability, a project that requires sustained political will, international cooperation, and investment, the kind of investment that is easy to defer until the moment it is too late. Now we need to address the elephant in the room, the conspiracy theories. Because for every official NASA press release assuring the public that Apophis poses no threat, there is a corner of the internet convinced that the truth is being hidden, that the asteroid is actually going to hit, that governments know and are covering it up, that the wealthy and powerful have already built bunkers and escape plans, while the rest of us are left in the dark. These narratives are pervasive, especially on platforms like YouTube, Reddit, and certain fringe websites. And while it is easy to dismiss them as paranoia or scientific illiteracy, there is actually something more interesting happening here. These conspiracies reveal a deeper crisis of trust between the public and scientific institutions, and understanding why people believe them is important, even if the beliefs themselves are unfounded. Let us start with the basic structure of most Apophis conspiracy theories. They go something like this. NASA and other space agencies have known for years that Apophis will hit Earth. They have run the calculations. They have seen the probabilities and they know it is coming. But they cannot tell the public because doing so would cause mass panic, economic collapse, and societal breakdown. So instead they issue carefully worded statements that technically do not lie but obscure the truth. They say things like, no threat for 100 years, or extremely low probability phrasing that leaves wiggle room for later revisions. Meanwhile, the global elite are quietly preparing, building underground shelters, stockpiling resources, securing their survival while the rest of us remain oblivious. When the impact finally happens, it will come as a shock to the masses, but not to those in the know. This narrative is compelling because it taps into existing anxieties about power, secrecy, and inequality. People already feel like they are not being told the truth about a lot of things. Climate change, economic instability, political corruption, the list goes on. So when they hear about a potentially dangerous asteroid, and then they hear reassurances from the same institutions they already distrust, those reassurances do not land. Instead, they sound like more of the same. elites telling comforting lies while quietly securing their own interests. Add to this the fact that asteroid science is complex, probabilistic, and filled with uncertainties, and you have a perfect breeding ground for conspiracy thinking. Because if even the experts admit there are unknowns, if they acknowledge that their models are not perfect, then maybe, just maybe, they're wrong. Or worse, maybe they are lying. The reality, of course, is far more mundane. Scientists are not hiding anything. They are doing their best to calculate the orbit of a chaotic object using imperfect data and incomplete models. When they say Apophis poses no threat for 100 years, they mean it. The calculations have been done, the uncertainties have been quantified, the risk has been assessed. But this does not mean there is zero uncertainty. Science is not about absolute certainty. It is about probabilities, confidence intervals, and best estimates. For Apophis, the best estimate is that it will not hit Earth in any foreseeable encounter. But best estimates can change as new data comes in, and that possibility, however remote, is what conspiracy theorists latch onto. There is also a psychological component to these conspiracies. Humans are pattern-seeking creatures. We want the world to make sense. We want to believe that major events have major causes and that someone somewhere is in control. The idea that a massive asteroid could just randomly happen to hit Earth with no warning and no one to blame is terrifying in a specific way. It suggests that the universe is indifferent, that catastrophic events are not orchestrated but accidental. Conspiracy theories offer an alternative. The event is not random, it is planned. There is a group pulling the strings, making decisions, controlling the outcome. And while that narrative is disturbing in its own right, it is also oddly comforting because it implies that the universe is not entirely chaotic. There is an order, even if that order is sinister. So how do we counter these narratives? Not by dismissing them outright. Condescension and ridicule only deepen the distrust. Instead, the answer is transparency. Scientists need to communicate not just their conclusions, but their uncertainties. They need to explain how the calculations are done, what the error bars mean, and why those error bars are shrinking as new data comes in. They need to acknowledge that models are imperfect, and that science is a process, not a finished product. And they need to do all of this in language that is accessible to people without advanced degrees in astrophysics. Because the more opaque the science seems, the more room there is for alternative explanations to take root. But there is also responsibility on the part of the public to engage with the information honestly, to recognize that uncertainty is not the same as deception, to understand that just because something is possible does not mean it is likely, and to resist the seductive simplicity of conspiracy narratives in favor of the messier, more complex truth. Apophis is not being hidden from you. The data is public. The calculations are peer-reviewed. The scientists are doing their jobs, and if new information emerges that changes the risk assessment, you will hear about it. Not because some whistleblower leaked it, but because that is how science works. Let us take a moment to entertain some scenarios that are, by all current evidence, extremely unlikely, but not physically impossible. These are not predictions. They are thought experiments, what-ifs, that stretch the boundaries of what we know and explore what could happen if the universe decided to surprise us. Because while the official line on Apophis is reassuring, the truth is that we live in a cosmos that occasionally does things we did not expect. And preparing for the unexpected, even in hypothetical terms, is not paranoia, it is prudence. Scenario 1. Apophis receives an unexpected impulse. Imagine that at some point between now and 2029, a small asteroid or comet fragment collides with Apophis. The object is tiny, maybe 10 meters across, barely large enough to leave a crater, but it hits just the right angle and velocity to change Apophis's trajectory by a few meters per second. That does not sound like much, but over the years remaining until the close approach, that tiny change compounds. By April 2029, Apophis's path has shifted just enough that instead of passing safely by Earth, it threads through one of the gravitational keyholes. The encounter with Earth in 2029 does not result in an impact, but it sets up a future collision in 2036 or 2068. We do not see this coming until it is too late to deflect. Scenario 2. Earth's gravity reshapes Apophis more dramatically than expected. Current models predict that the 2029 flyby will cause some tidal effects on the asteroid's surface and rotation. But what if those effects are stronger than anticipated? What if Apophis is not a solid rock, but a loosely bound rubble pile, and the gravitational stress during the close approach causes it to partially disintegrate? Chunks of material break off, forming a debris cloud. Some of those chunks remain gravitationally bound to the main body, but others drift away on slightly different orbits. Now, instead of tracking one asteroid, we are tracking dozens, and some of those fragments might be on trajectories that bring them dangerously close to Earth in future encounters. Scenario 3. The Yarkovsky Effect is stronger than we calculated. We think we have measured it accurately, but our measurement depends on assumptions about the asteroid's surface properties. What if those assumptions are wrong? What if Apophis has an unusually dark, heat-absorbing surface that amplifies the thermal radiation pressure? Or what if its rotation rate changes due to the Yarkovsky effect, altering the direction and magnitude of the Yarkovsky thrust? Over decades, this stronger-than-expected force pushes Apophis onto a different path, one that our current models did not anticipate. By the time we realize what is happening, the window for deflection has closed. Scenario 4. A binary companion is discovered. Most of our observations of Apophis have focused on the main body. But what if it is not alone? What if there is a smaller object, maybe 50 or 100 meters across, orbiting Apophis like a moon? Such a companion could have been missed in earlier observations if it is dark and close to the main asteroid. Binary asteroids are not uncommon in the solar system, and if Apophis has a companion, the dynamics become vastly more complicated. The two objects pull on each other gravitationally, affecting both of their orbits, and during the 2029 flyby, Earth's gravity could disrupt that binary system, sending the smaller object on an unpredictable trajectory, maybe toward us. Scenario 5. Planetary defense technology fails when we need it. Let us imagine that we do detect a threatening asteroid, not Apophis, but some other object on a collision course with Earth. We have 10 years of warning, which should be enough time to launch a deflection mission. We build the spacecraft, we launch it, and it travels to the asteroid. But when it arrives, something goes wrong. The spacecraft's navigation system malfunctions, and instead of hitting the asteroid at the optimal angle, it glances off the surface, transferring minimal momentum. Or worse, the impact causes the asteroid to fragment, creating multiple smaller threats instead of one large one. Or maybe the deflection works, but not as well as predicted, and the asteroid is only partially redirected. Instead of missing Earth entirely, it grazes the atmosphere, breaking apart and showering the surface with debris. These scenarios are not likely. They require specific combinations of events, each individually improbable to occur in sequence. But the point is not to scare you. The point is to illustrate that orbital mechanics is a chaotic system, and chaotic systems are by definition sensitive to small perturbations. We can model the big forces, we can account for the major interactions, but there are always unknowns, always variables we have not measured, always possibilities we have not considered. And while our models are good, they are not perfect. The universe has a way of reminding us of that fact, usually at the most inconvenient times. So what do we do with this knowledge? We prepare, we keep watching, we refine our models, we improve our detection capabilities, we develop and test deflection technologies, and we accept that some level of uncertainty is unavoidable. The cosmos does not owe us certainty, it does not owe us safety, but it does offer us the opportunity to learn, to adapt, and to protect ourselves as best we can. And that, in the end, is all we can ask for. The future we are building is one of vigilant awareness. It is a future where the close pass of Apophis is not an ending, but a catalyst for better telescopes, for faster computers, for stronger international bonds, and for a deeper public understanding of our place in a dynamic solar system. We're building the capacity to turn fear into focus and uncertainty into action. The story of Apophis is the story of humanity growing up, looking squarely at the dangers in the void, and deciding to become the guardians of our own world.